Hi, I'm Jonathan Lee, a senior researcher at Microsoft Research. This work was joint with Kirill Nikitin from EPFL and Srinath Setty, also from MSR. The talk will be about Piperine, a system for reducing the end-to-end costs of real-world, highly replicated systems without weakening their safety or liveness guarantees. Blockchains are a popular example of a highly replicated system, where the nodes of such a system are mutually untrusting. Transaction execution in these systems is normally comprised of two phases. First, the nodes use some consensus algorithm to decide a list of possibly invalid transactions that they will attempt to execute. Then, each node applies the transactions in order to a local copy of the system state, discarding any which are invalid. In addition to replicating the state, this approach is replicating lists of transactions and transaction execution. In real systems, there may be tens or hundreds of thousands of nodes, so there are strong incentives to avoid this kind of work. This problem is not new, and in the blockchain space, there are many proposals to mitigate it. There are two main approaches in the literature. One broad approach is to modify the consensus algorithm. This seeks to trust a smaller number of nodes that will reach consensus on and execute some valid transaction. A typical node then doesn't have to check or re-execute most transactions, but only a few. However, in general, this weakens the safety guarantees of the overall system, as this smaller set of nodes is trusted for correctness. Sometimes that is further patched by talking about incentives or something like this, but the core point remains. Another broad line of work attempts to execute certain classes of transaction without mutating the global state. In the blockchain context, this is the core reason that moving state off-chain has such performance benefits. However, it's not easy to ensure that this off-chain information can be recovered, and so in general the liveness guarantees are weakened. The techniques we're going to describe are general and apply to any replicated state machine, and don't alter the safety or liveness properties, so our techniques can be applied in tandem with those approaches if you want. Our system, Piperine, goes after the problem more directly. The core observation is that prior work allows us to delegate the execution of a stateful computation to a prover P and check it with some separate verifier V. So we might hope that this prover can collect some transactions, execute them, and provide a proof of their correct execution. The unmodified consensus mechanism would then be used to choose some candidate proof. Each node then verifies the proof, and if the proof is correct, they update their stored state. Since only the verification is re-executed, we might hope to reduce the re-execution costs. This is similar in principle to other works that attempt to provide privacy. Of course, in our context, we can't rely on the prover for liveness, and so the prover has to make all the effects of the transactions on the public state public. In this sense, privacy and liveness are necessarily in tension. In fact, we're actually going to show some surprising extra features. First, whilst the prover needs to know a complete transaction in order to execute it, the verifiers only need to know the impact of that transaction on persistent state. In a typical scenario, transactions contain more information, for example signatures, which can be discarded. So we can actually reduce the amount of information about which the RSM has to reach consensus. We can also allow for concurrent transaction execution on the prover, which allows transaction execution to scale out. In the rest of the talk, I'm going to provide some background on a prior system, SPICE, which we use for proving correct execution of stateful computations. I'll also discuss how we extended this prior work to build Piperine and discuss a few experimental results. Firstly, we're going to discuss probabilistically checkable proofs, or more accurately, their SNARK descendants. These allow for the delegation of stateless, non-deterministic computations. This means there's some program which is shared between the prover and the verifier. The verifier knows the inputs and outputs of this program, whilst the prover is going to choose some additional hints that are used internally to the program. For example, here we have a square root function. The prover is actually going to supply the square root as a hint, and the function is just checking that the square of the alleged square root is what it's supposed to be. So the key point is that the prover can show the verifier a succinct proof that the program was correctly executed, given these unknown hints. Modern SNARKs generally act on arithmetic constraints over a finite field. Many programs can be compiled into this form, as you see on the right. In SPICE, which was presented at OSDI 2018, we extended zero-knowledge SNARKs to provide a verifiable state machine abstraction. This is a delegated stateful computation, where the state is abstracted as a key value store. SPICE also provides a toolchain allowing for the state machine transitions to be specified in a large subset of C. However, even SPICE doesn't solve our problems directly. Most importantly, SPICE delegates all the state to the prover, so in our context, the liveness would depend entirely on the prover. The verifiers actually know only a digest of the state. Since we'll be modifying how state is handled to go from SPICE to Piperine, we're going to do a brief deep dive on how state is already handled in SPICE. Within each computation, SPICE tracks the state logically by a set of timestamped reads and writes. These sets are compressed with an incremental hash function, which has the property that the hash of the union of two sets can be computed quickly from the hashes of the sets individually. This pair, the hash of the read set and the hash of the write set, is then used analogously to a Merkle root in some other systems. SPICE manages to reduce the correctness of operations on the key-value store to a certain global invariant. In particular, the set of reads must be a subset of the set of writes, and in that difference, the unread writes, each key can appear at most once. So SPICE's prover will execute some collection of transactions, and from time to time it audits the key-value store by showing that this invariant has been maintained. This is pretty costly. The state that is shown inside this audit is as large as the original key-value store, but hopefully you amortize it over many transactions. Conveniently, this allows the stateful computations and the audit to be represented as some non-deterministic stateless computations, and the verifier also has to check that certain sums of incremental hashes are equal, but that's pretty cheap. The stateless computations are then all proven correct using zero-knowledge SNARKS. We'll now turn to some of the extra steps that were required to go from SPICE to Piperine. In the context of Piperine, the fundamental additional requirement over and above what SPICE provides is that the prover must make the new state public. This new state must provably correspond to the state that was audited in SPICE. This is not as straightforward as it might seem. A first attempt would be to simply reveal the entire state that was used during the audit. However, as we saw, this would require transmitting the entire system state at every audit, which is far too costly. In the alternate, we might ask that each transaction reveal the local changes that it made to the state. However, multiple transactions might update the same state, for example when a payment is routed through an intermediary. So without an ordering of the individual transactions, we can't take this local data and combine it to find the final state. Unfortunately, SPICE doesn't provide a concrete ordering of all the transactions, and this is fundamental to allowing concurrency in the prover. Even if this were added somehow, the approach cannot be optimal for network costs, because if a particular key is written multiple times, then we would see multiple writes to that key in this transcript, but we only need to know the final value. Instead, we make the following observation. Since in each audit, the verifier learns the hash of the prover's current state, the verifier actually knows the hash both of the states S and S' before and after the transactions that the prover has executed. The prover also knows how to insert, delete, and update values in the store to affect this change, and knows what data was overwritten by those changes. Finally, and here's the key difference with a Merkle root, since the hash function is incremental, the hash of S' should be the hash of S plus the hash of all the new state minus the hash of all the overwritten state. So the prover is going to provide a transcript delta of all the changes and show that it knows some overwritten state, which is consistent with that sum constraint. Since the hash function is collision resistant, if these checks all pass, the verifier can deduce that applying delta to its own state S will update it to S'. Importantly, any part of the state which is modified many times during this batch of transactions, for example blocks or hot data, only is going to appear once. Any part of the original transactions that don't mutate state, such as signatures, don't appear at all. So overall we have the following flow. The prover is going to execute some arbitrarily large batch of transactions, modifying a local copy of their system state. The prover will then audit their local state as they would in SPICE, thereby showing that the transactions were executed correctly and that they know the eventual state of the system. Then the prover is going to reveal a transcript of the state changes and prove that this transcript, applied to the original state, produces the audited state. The verifiers are going to pick all this up, and if all those checks pass, then they will apply those state changes directly. While state extraction provides an in-principle solution to our problem, there are some further important practical performance optimizations that should be mentioned. We don't really have time to substantively discuss these or their detailed impact, so see the paper for all the details. First, we have to pick a signature scheme that is efficiently verifiable in an arithmetic circuit. This reduces the concrete costs of signature verification by orders of magnitude. Second, we batch transactions on the prover, which means that the number of proofs that must be verified is substantially reduced. Finally, even with this batching, we would naively generate functions with quite a lot of inputs and outputs, and those are somewhat expensive to verify. Instead, we're going to hash all the inputs and outputs of a batch, so that the snark is applied to a function with very few public parameters. This does mean that the verifiers have to do some additional hashing, but that's cheaper than the marginal operations they would have to do to handle additional I/O. One of our tests of Piperine will be in the context of Ethereum, so I'm going to introduce the key features of Ethereum that we'll need now. First, Whilst you can consider Ethereum to be a single replicated state machine, we'll be looking at it as a platform for defining some contracts, and we're going to treat those contracts as independent replicated systems. So how does this work? Ethereum defines a virtual machine, the EVM, which has a highly complex set of instructions. These range in complexity from simple stack manipulations and arithmetic up to persistent storage operations, complex hash functions, and even pairing computations on specific curves. The analog of execution time in the EVM is an abstract thing called gas. Simple operations might cost less than 10 gas, whilst complex ones can cost over 100,000. This obviously has to be translated into something that we can compare to other systems, so we'll mention the dollar costs here. The dollar cost of gas fluctuates quite wildly. It has been as high as $100 for a million gas, but in recent times, a more typical value is more like $1 for a million gas. There's also a limit on the total gas consumption in a single block, which means that highly complex operations must be split into multiple pieces. Given this context, when we test Piperine on Ethereum, we'll be working in the following setting. First, we're only going to re-implement one contract, an ERC20 token. This class of contract is responsible for about a half of all Ethereum transactions. We're also going to completely break interoperability with the rest of Ethereum. We're changing the signature scheme to one that is similar in security but convenient for us, and we're not going to approach the question of how to make calls from one contract to another, which Ethereum allows. For us, the prover is going to be thought of as run by some untrusted party. We're not going to discuss how to incentivize this party, but as we'll see, the prover costs are quite low. However, there aren't any fundamental liveness issues there. Supposing that some party was to stop running the prover, any person could start their own prover and start submitting new valid transactions, for example, to recover their funds. So what did we actually have to build? Well, first we built Piperine atop Spice, which internally uses libsnark to implement the Groth16 snark. This took about 375 lines of C in some libraries. Secondly, we implemented additional orchestration for Piperine in about 725 lines of Python. This is used to do parallelization on the prover, and it manages the additional auditing for the prover. To demonstrate Piperine as it might apply to a popular kind of state machine on Ethereum, we implemented a payment processing service exposing the ERC20 interface. This took about 380 lines of C. We also implemented the Piperine verifier as a smart contract in 500 lines of Solidity, the standard language for writing state machines on Ethereum. So now we can turn to our experimental results. Our main two questions for the evaluation were as follows. First, in what possibly synthetic regime can Piperine's techniques reduce the overall cost? And second, do any existing large-scale replicated state machines fall into that regime? For our testing purposes, all of our native executables, such as the prover or the x86 verifier that we'll discuss, would run on a cluster of Azure VMs. The prover was parallelized, the verifier was single-threaded. To answer the first question, we studied the resource costs in terms of CPU and network of both the prover and verifier running as native executables. In this experiment, we're not implementing any RSM, and we're simply studying the resource costs of transaction execution. To be conservative, we compared to a baseline that does no non-trivial transaction processing and simply checks that the transactions are signed. This is a minimal operation that must be performed on any transaction when you have Byzantine failures. Our Piperine implementation implements the full ERC20 interface, extracts state, and does all the other things that are necessary. Since the batch size is a key parameter, we're going to allow that to vary. We're going to measure the prover, verifier, and baseline performance against a synthetic workload of create and transfer operations, modeled after the BAT token. In terms of CPU cost, we see that the Piperine prover and verifier both improve as the batch size increases, whilst the baseline does not. The prover remains concretely some orders of magnitude more expensive than the baseline. Now, recall, our overall aim is to reduce the cost of running a replicated system, so it's natural to ask how many nodes must exist for the per node savings to exceed the cost of the prover. Whenever the verifier is cheaper than baseline, this is what we computed. So for batches of 64 transactions or more, the Piperine verifier was cheaper than the baseline, and for large batches, the number of replicas required to break even is reduced to about 10,000. This is comparable in size to some blockchain networks. We also find that Piperine generally reduces network costs. For small batches, the order 1 contribution from sending proofs is quite large, but this is quickly amortized. As the batch size continues to grow, however, additional savings emerge. Since we replace a batch of transactions with a specification of its overall effect, additional writes to data that have already been written to in this batch have no marginal cost. So growing the batch size provides additional opportunities for compression, particularly if the underlying workload has any hot data in it. For large batch sizes against this workload, we managed to save about a factor of 3, which could be significant in the blockchain setting. To evaluate whether the cost of existing large-scale replicated state machines might be reduced by using Piperine, we compared end-to-end costs between our Piperine verifier running on Ethereum and a naive implementation of the ERC20 interface. As in the earlier experiment, we used a large synthetic workload based on the BAT token. To compare overall costs, we convert prover time and verify gas consumption into dollars and measure the size of the transaction sent to Ethereum. Our machines cost about 20 cents per core hour. As can be seen, the per transaction costs are reduced by a factor of over 5, whilst network use is reduced by almost a factor of 3. The dollar cost of the verifier is in fact still substantially more than that of the prover, which means that we can afford to be more inefficient in future on the prover without changing our overall conclusion substantially. In summary, our main conclusion is that cryptographic proof machinery can actually reduce costs of real-world systems rather than it being something that's forced onto us by security or privacy requirements. Secondly, the particular techniques in Piperine allow for replicated state machines to avoid replicated execution without having to compromise on safety or liveness guarantees. And perhaps surprisingly, we're also enabling concurrency and, in general, weak consistency models for state in an open, permissionless replicated state machine.